Hey there, Calc Kids. So here is your homework that you had from last class. Sorry I'm not there today to go over this with you, but make sure you come back to class with questions. All right, so here it is. We started talking about this antiderivative, which is the opposite of finding the derivative. Anytime you see this word anti, you know you're talking about the opposite of finding the derivative, which is what we call integration and taking the integral. All right, so if this was our original function and we were looking at finding the area curve between this lower limit and this upper limit, what we found out last time was that the derivative of my original function is equal to this rate. So keep in mind that this was the equation of my rate. So when I want to find the antiderivative, that's going to be my original function, it helps to know that the derivative of this function was, and I just put my x inside. So all we are doing right here is that is my rate, and I'm rewriting this function in terms of the original function's derivative. So by putting x in, there's no variable. So the rate of this function is just 5. Today we're going to be taking this and putting it into terms of what my original function was. So think about what happens when I take the derivative that I end up with just a constant. All right, so all I'm doing here is I'm putting my upper bound, my x variable in, and that is my derivative. All I'm doing is taking my upper bound and I'm putting it into my function. Upper bound into my function. So what's interesting here is when I put this x squared into this function, I have to think about what the derivative of that is, and that was where we talked about having that chain rule, where when I put this value in here, I need to also add the derivative of what's inside. And we're going to talk about how that represents that dt. All right, so again, my x squared goes in for my t, and then I have that chain rule. When I look at 7, I put my sine of x in for that variable t, and then the derivative of what's inside. I'm going to go ahead and put my x squared in there, the derivative of what's inside. So each of these chain rule examples is what is represented by that dt. Here's 10, 11, and 12. Star or circle any ones that you want to talk about when we see each other again on Thursday. 13, 14, and 15. 16 and 17. All right, so flipping over and checking out the back, if g of x is equal to the derivative of this, and remember taking the derivative of the integral, that's where we end up with that inverse conversation, and those two actions undo each other. So I'm going to go ahead and take my x and plug it in. So my original function is this. So when I want to know what g of 4 or of negative 4 is, all I'm going to do here is put negative 4 in for my x, and then therefore I can go ahead and solve. For number 19, the graph of a function f on a closed interval is shown. Let h of x equal the integral, the area under the curve of this function along this interval from 0 to 6. So let's go ahead and figure out what it is we're talking about. I'm looking at this graph, and this graph is the rate. So f of t is the new name for the rate, but I know it's also going to be the derivative. So when I'm looking at my original function h sub t, let h sub t equal the integral of this graph. So this is my original, h of x is my original, h prime or f of t is my rate. So it wants to know, find h prime of 3. This graph is my rate. There's h prime of 3. 3 goes in and 0 comes out. All right, so here is a super hard one. No big deal if your paper's blank on this one. But we can go ahead and talk about, so here is this rate curve. The figure above shows the region A, which is bound by the x and y axis, and this graph. So here is this graph f of x, 1 minus cosine of x over x, for all the values of x is greater than 0. And I have this vertical line at x is equal to b. Okay. If b increases at a rate of pi over 2 units per second, how fast is the area of the region increasing? So this goes back to those related rates and those problems we were doing where we were looking at how fast is our function changing. So our area under the curve is equal to the integration from 0 up to b. So this is what we're talking about when we're talking about the sum of all the little rectangles. So if you think about drawing all these little rectangles, again, I'm looking at this graph is the graph that's a rate, and I'm thinking about finding the integral, which is the sum of all these little triangles that help me calculate the area. B is moving this way at a rate of pi over 2 units, whatever my y units are that I'm measuring, per second. Second is my time. So B is sliding this way. And I want to know, how is this area changing? So when I take the derivative of this integral, remember those are inverses and they cancel each other out. So think about that when we talked about tying and untying your shoes. So all I'm left here is this original function. When I go to take the derivative, this is my rate. And my rate, I know, is changing at pi over 2 units per second. So now it becomes a matter of just plugging in where b is at that moment. And they say where b is equal to the cosine of pi over 3. Well, the cosine of pi over 3 is 1/2. Here it is here. So when I plug that in, 1 minus 1/2 over pi over 3 times pi over 2. So I'm going to go ahead and 1 minus 1/2 is 1/2. Divide by pi over 3 is the same as multiplying by 3 over pi times that. And that's how I get 3/4. How fast is the area increasing? It's increasing at 3/4 units per second. It's area, so it's units squared. So if you didn't get that, it's okay. But it's still fun to talk about it. All right, make sure you ask the substitute to now pass out to you this worksheet, and this will be our next lesson.